Welcome back for another deep dive. Today, we're going to be looking at something that might just change how we think about large language models. So get this, it seems like there's a pattern emerging in how much power we can actually pack into these LLMs. It's almost like a Moore's law, but for AI.
Yeah, it's really interesting stuff. And what we're focusing on today is called capability density.
That's ability density.
Yeah, and it's all laid out in this paper, Densing Law of LLMs.
Okay.
It's by Chaojun Xiao, Ji Kai, Weilin Zhao, Guoyang Zheng, Bionglin, Ji Zhou, Xi Zheng, Xu Han, Juan Liu, and Maosong Sun.
So are we saying it's not just about making these models bigger and bigger anymore?
Exactly. Capability density, you see, it's a way to measure how much performance you can squeeze out of each parameter in the model. It's about efficiency, how well those parameters are working, essentially.
Okay, so how do they actually go about calculating this capability density?
Well, what they do is they compare the LLM to a reference model, and they work out the smallest number of parameters that the reference model would need to have to match the performance of the LLM that they're evaluating. And that number, that becomes the effective parameter size.
So they're figuring out the minimum size that reference model would have to be to do the same job, basically.
Exactly. And then they divide that effective parameter size by the LLM's actual size. And that gives you the capability density.
Got it. So a higher density means we've got a more efficient LLM, right? We're getting more bang for our buck, so to speak.
You got it. And what's really fascinating is that the authors of this paper have observed a trend that they're calling the densing law.
Ooh, a new law of the AI world. Okay, tell me more. What does it say?
It suggests that the maximum capability density of these LLMs is growing exponentially, doubling roughly every 3.3 months.
Hold on, every 3.3 months? That's incredibly fast. Are you sure?
That's what their analysis of 29 widely used open source pre-trained base LLMs released since February 2023 shows.
Wow.
They even have a formula to represent this, LMX plus B.
Okay, let's break that down a bit. What does each part of that formula represent?
So ROMX, that's the maximum capability density at a given time, which is 8. And then A and B, those are constants that they've got from their data analysis.
Okay.
So the formula basically shows how that maximum capability density increases over time.
Okay, I think I'm following. So how do they test all these different LLMs to figure all this out? They must have put them through some pretty rigorous tests.
Oh, they did. They used five well-established benchmarks to evaluate these LLMs: MMLU, BBH, Math, Human Eval, and MBPP.
Wow, that's like an LLM decathlon.
It is.
What do these tests actually involve? Give us some examples.
We'll take the MMLU benchmark, for instance. It tests a model's understanding and reasoning across 57 multiple-choice tasks. It covers a wide range of subjects like elementary mathematics, U.S. history, even computer science and law.
So they're really pushing these LLMs to their limits, not just seeing if they can write a poem or something.
Exactly. These tests are designed to see if they can solve complex problems and show real understanding. And these tests were designed to measure the LLM's ability to perform in a few-shot, in-context learning setting, meaning, they only had a limited number of examples to learn from before tackling the test.
Oh, wow. So it's like they're testing how quickly these LLMs can learn and adapt to new challenges.
Yes, exactly.
That's pretty impressive.
Yeah.
What about the process of figuring out the density itself? How did they come up with those numbers?
Right, so they had a two-step process for that.
Okay.
First, they estimated the loss on the test sets for each LLM. Loss. Think of it as a measure of how far off the LLM's predictions are from the actual correct answers.
Okay, so the lower the loss, the better the LLM is doing on the test.
Yeah, exactly. And to estimate this loss, they trained a separate set of smaller models with varying parameter sizes and amounts of training data. These smaller models, they call them scaling models. And they were trained using the mini CPM 34B training corpus.
Why did they use that particular corpus?
Well, mini CPM 34B is known for being very efficient, especially for edge computing. Running on devices with limited resources. So it was a good baseline to understand how performance relates to model size and data.
Interesting. So they used these smaller models as the kind of yardstick to measure the larger LLMs against.
You could put it that way. And they were very meticulous about making sure it was a fair comparison. They used a consistent model architecture for these scaling models with features like grouped query attention and gated feed-forward layers.
Okay, hold on. Those sound pretty technical. Can you break those down a little bit?
Sure. So group query attention, it's a way to make the model more efficient at processing information by dividing the input into smaller chunks and focusing on the most relevant parts. And gated feed-forward layers are like filters that help the model learn complex patterns.
Got it. So they used a carefully controlled setup to estimate the loss of those larger LLMs. And then what was the second step?
The second step was all about performance estimation. For this, they used well-trained mini CPM3 models and snapshots of their training progress. These had parameter sizes ranging from half a billion to tens of billions.
So they brought in another set of models. What was the purpose of these ones?
These mini CPM3 models, they share the same vocabulary as the scaling models, but they've got different parameter sizes and were trained on different data sets. This let them compare performance across a broader range of model sizes and training conditions.
I see. So they're really trying to get a comprehensive picture of how performance scales with different model sizes and training approaches.
Exactly. And they use this clever two-step method to predict what they call downstream performance based on the loss on the test sets.
Okay, and what does downstream performance mean in this context?
Downstream performance, it refers to how well the LLM performs on specific tasks, like the ones we talked about earlier. MMLU, BBH, all those. Basically, it's the real measure of the LLM's capabilities.
So they're trying to predict how well these LLMs will perform in the real world based on their loss values.
Exactly. First, they use reference models to establish a relationship between parameter size and loss on the test set. That gives them an idea of how loss behaves as models get bigger.
But it sounds like there's a bit of a challenge here. Why couldn't they just directly estimate downstream performance using these reference models?
Well, because training large reference models with enough computational power for accurate estimation, it's very resource intensive.
Makes sense.
So they used open source models to map the relationship between loss and actual downstream performance.
Ah, clever. They're using readily available data to bridge that gap.
Precisely. And to represent this relationship, they chose a sigmoid function, which essentially squishes all those input values into a range between 0 and 1.
Okay, and why a sigmoid function specifically?
Well, a sigmoid function works well in this case because performance on most downstream tasks is bounded. There's a limit to how well a model can perform. And a sigmoid function reflects that. It creates a curve that levels off as performance reaches its maximum.
So they're taking into account the real-world limitations of LLM performance.
Very
clever. So how did all of this effort translate into actual results? What did they find?
Well, their two-step estimation process revealed some very interesting findings.
Okay, I'm all ears. What did they discover?
As that loss on the test instances decreased, they saw, well, a significant improvement in performance.
Okay.
And it followed like a sigmoidal curve.
Right.
They also found a power law relationship between the loss itself and the number of parameters and training tokens. These relationships actually allowed them to predict the downstream performance of LLMs based on those loss values.
So the lower the loss, the better the performance. But they also found that this relationship isn't linear.
Right. It's more nuanced than just saying, smaller loss always equals better performance. There's this interplay between loss, model size, and training data.
Fascinating. Okay, so did their findings actually support the idea that LLM density has been on the rise?
They did. Their analysis showed very clearly that the density of LLMs has increased a lot, dramatically even over time.
Right.
And this increase, it's likely due to a combination of factors, including the growth of that pre-training data and improvements in data quality.
Can you give us some examples of this density increase? Like how much has density actually changed?
Sure. If you take Llama 1, for example, released back in February 2023,
Right.
it had a density below 0.1.
Okay.
Compare that to more recent models like Gemma 29B and Mini CPM 3.4B, both from 2024.
Right.
Those have hit densities of 3.
Well, a 30-fold increase in just over a year.
Yeah. But here's the thing. Their research also showed that just getting better performance, it doesn't always mean you get better density.
So bigger and better doesn't automatically mean more efficient.
Right. There are other things at play. Take Llama 3.1 405B, for example.
Right.
Released August 2024. It's a massive model, achieving state-of-the-art performance among open-source models, but it doesn't have the highest density.
If it's so powerful, why wouldn't it be the most efficient?
Well, with these super large models like Llama 3.1 4005B, it gets hard to fully optimize the training because of limitations in computational resources and the amount of pre-training data. It's like trying to perfectly train a star athlete You need that special facility and a huge support team to unlock their potential.
So you can't just keep making these models bigger and expect everything else to fall into place.
Exactly. There are trade-offs. Now, to capture this trend of increasing LLM density, they fit a linear function to their data. They assumed that the logarithmic value of the maximum density increases linearly over time.
Can you remind us what that formula looks like again?
Sure, it's ln Hmax at plus b,
Right.
where max is the maximum capability density, t is time, and a and b are constants from their data.
And what did this formula tell them about the rate of this density increase?
It showed that the density of LLMs is doubling about every 95 days,
Wow.
which is a very fast rate of improvement.
That's faster than the seasons are changing. And they're calling this trend the densing law.
Yes, they are, because this growth in model density is similar to the principles of Moore's law in chip development.
Okay, I see the connection now. Moore's law has driven this incredible progress in computing power. Are they suggesting that the densing law could have a similar impact on how we develop LLMs?
Yes, and they've even outlined several corollaries or consequences that stem from this law.
Let's hear about those. What's the first one?
The first one is that inference costs for LLMs with equivalent downstream performance are decreasing exponentially.
Quick reminder, what are inference costs again?
Inference costs, those are the computational resources you need to run an LLM and get those results, like generating text, answering questions.
Right, so this is saying that it's becoming cheaper to use LLMs that achieve a certain level of performance. Why is that?
Well, it makes sense. With increasing density, we can get that same performance with smaller, more efficient models.
Right.
And smaller models require less computational power to run, so that means lower costs.
It's like finding a way to build a car that gets the same gas mileage but uses half the gas.
Yeah.
That's a huge saving.
Yeah.
Did they find any real-world examples to back this up?
They did. They looked at the API pricing of LLMs that have done better than GPT 3.5 since it was released in December 2022. They found that prices have been dropping exponentially.
So the cost of using these really powerful LLMs is going down. What kind of price drops are we talking about?
Well, for instance, in December 2022, using GPT 3.5 cost $20 for 1 million tokens. By August 2024, Gemini 1.5 Flash, a more powerful model, could handle the same workload for just 7.5 cents.
Wow, that's a huge reduction in just under 2 years.
It is, and it's happening even faster than the rate at which LLM density is increasing.
Really?
This suggests that advancements in the infrastructure used to run these models, that's playing a big role in driving down those costs too.
So it's not just about the models themselves becoming more efficient, but also the hardware and software that runs them.
Exactly. Things like memory access speed for self-attention layers, which are a key part of LLMs, and sparse computation for those feed-forward networks. Those are all contributing to reducing those inference costs.
It sounds like a lot of different pieces are coming together to make LLMs more accessible and affordable. Okay, what about that second corollary? What's that one all about?
The second corollary links the densing law with Moore's law. It suggests that the effective parameter size of LLMs that can run on chips of the same area will increase exponentially.
Okay, let's unpack that. We've talked about the densing law. Reminder, what is Moore's law again?
Moore's law says that the number of transistors that can be placed on an integrated circuit that doubles roughly every 2 years. It's why we've seen this huge growth in computing power.
Right, so this corollary is basically saying that as those chips become more powerful, thanks to Moore's law, we'll be able to run even more efficient LLMs on them because of that densing law.
Exactly. It's like a double whammy of progress. If both of these laws hold true, we could see LLMs with super high effective parameter sizes running on everyday devices.
That's mind-blowing.
Yeah.
Are there any other corollaries they've outlined?
Yes, there are. The third corollary focuses on something specific that seems to have sped up LLM development. The release of ChatGPT back in November 2022.
ChatGPT. That was the moment the whole world sort of woke up to the power of LLMs, wasn't it?
It was a big moment. And the authors found that the growth rate of LLM density, it sped up a lot after ChatGPT came out.
How much did it increase by?
They found a 50% jump.
Wow, that's significant. So ChatGPT didn't just introduce the world to LLMs, it also seems to have accelerated their development. Why do they think this happened?
Well, they put it down to a couple of key factors. First, ChatGPT's success led to a lot of investment in LLM research and development.
It makes sense. When something shows that much promise, everyone wants a piece of the action.
Right. The second factor was the rise of those high-quality open-source models. ChatGPT's release, it seemed to have inspired a lot of researchers to make their own models and tools publicly available. This made LLM technology more accessible, leading to more experimentation and innovation.
It's incredible how one event can have such a ripple effect. So, faster density increases, thanks to ChatGPT. What about the fourth corollary?
So yeah, the fourth corollary, it's about a common idea people have about making LLMs more efficient. They think that compressing those models, that it always makes the density better.
You mean techniques like pruning and distillation? The ones that make the models smaller?
Right, those are the ones. And while they can be good at making a model smaller and faster, they don't always mean higher density.
That's surprising. Why wouldn't a smaller model just naturally be more efficient?
Well, it comes down to how you do the compression. If you're not careful, you can lose important information or reduce the model's ability to learn. It's like trying to fit all your stuff into a smaller suitcase. If you just cram it in there, you could end up with broken things in a suitcase that's still hard to close.
So it's not just about shrinking the model, it's about doing it in a smart way that keeps its ability to learn and do its job.
That's it. And this highlights the need for more research into compression techniques that focus on keeping that density high, or even making it better. Now, the fifth and final corollary, this one's pretty interesting. It challenges the idea of just focusing on performance when we're developing LLMs.
So we can't just make them bigger and more powerful and call it a day. There's more to it than that.
Right. They argue that we need to look at it more holistically, thinking about density as a key metric along with performance.
Okay, I'm intrigued, but why? Why is density so important?
And they make a good point. Because LLM technology is moving so fast, the lifespan of each model gets shorter. A new model could come out in just a few months with similar performance but lower costs.
So if we're always chasing the newest, most powerful model, we could be missing out on the benefits of those smaller, more efficient ones.
Exactly. They're proposing something called a green scaling law. It's a framework that focuses on developing LLMs that deliver the best performance with the lowest computational cost.
So they're pushing for a more sustainable approach to LLM development, one that thinks about the environment and accessibility, not just performance.
That's a great way to put it. They believe that this density optimal training, that it's essential for sustainable development in the LLM field. And that covers all the corollaries from the paper.
Wow, this deep dive into the densing law has been fascinating.
Yeah.
It seems like we're at the beginning of a big shift in how we think about and create these LLMs. Efficiency and density, those are the new stars of the show.
Definitely. The densing law has given us a new way to look at the future of this technology, a future where LLMs are powerful but also more accessible and sustainable.
It's been a great journey through this research, and we've only just touched the surface. I can't wait to see how this densing law shapes the future of LLMs and what other groundbreaking research comes out in this field.
Me too. It's a really exciting time to be following all of this.
It really is. Well, that brings our deep dive for today to a close. We've covered a lot, from understanding what capability density is to exploring the implications of the densing law and its 5 corollaries. If you're interested in learning more, we've included links to the research paper and other resources in the show notes.
Yeah, be sure to check those out. The paper goes into much more detail, including the specific algorithms and statistical methods they use.
And who knows what the future holds? Maybe in a few months we'll have even more groundbreaking research to talk about. Until next time, keep exploring, keep learning, and keep pushing the limits of what's possible with AI.